All right, today we're going to pull back the curtain on the invisible world that powers, well, pretty much everything. We're going to meet the three fundamental, unsung heroes hiding inside every single electronic device you own. So, what do they have in common? I mean, think about it for a second. One fits in the palm of your hand, the other spans entire countries. You couldn't get much more different, right? Well, here's the crazy part. They're both built on the exact same fundamental principles, using the exact same core parts. And the answer is passive components. Yeah, it's a simple name, but it's a super powerful idea. See, unlike a battery or a generator, these guys don't create power. Not at all. Instead, their whole job is to manage it, to wrangle it. They either dissipate it, kind of like hitting the brakes on a car, or they store it up for later. They are, and I'm not kidding here, the absolute bedrock of all electronics.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, so let's meet the first and most common member of this trio, the resistor. And its whole deal? It's all about control. You know that every electrical circuit has a current, which is just the flow of electricity. Well, a resistor's entire purpose in life is to push back against that flow, to create a very specific, calculated amount of opposition, which might sound a little weird. I mean, why would you ever want to slow electricity down? The classic analogy works best here. Imagine your circuit is a water pipe. A resistor is like a deliberately narrow section in that pipe, a bottleneck. It doesn't stop the water completely, but it totally controls how much can squeeze through at any one time. And this is absolutely crucial. It's how you protect delicate little things, like an LED, from getting blasted with too much current and just, poof, burning out. So, to recap, resistors control current by getting rid of any excess energy as a tiny bit of heat. We measure this resistance in a unit called the ohm, and if you ever see a circuit diagram, it's that little zigzag line. Simple as that. Next up, we have the capacitor. Now, if resistors are the brakes, you can think of capacitors as these tiny, super fast, rechargeable batteries. They're all about storing up energy and then letting it go in a quick burst. And what's so cool about a capacitor is just how simple it is. I mean, look, it's basically just two metal plates with a little insulating gap in between. That's it. But that simple setup gives it this amazing property called capacitance, the ability to hold an electrical charge. It's like creating a tiny controlled lightning storm right there on the circuit board. Yeah, the best way to picture it is that tiny battery that can charge up and then discharge in a split second. We're not talking about long-term power here. This is all about delivering a quick, powerful punch of energy. The flash on an old camera? That's a perfect example. The capacitor charges up, waits, and then bam, it dumps all that energy at once to create the brilliant flash. So here's how it works. It's a simple three-step dance. First, you apply some voltage and charge starts to build up on those plates. Second, that stored charge creates an electric field. That's where the energy is actually held. And third, the second the circuit needs that energy, the capacitor just lets it all go at once. Charge, store, release. It's a simple but incredibly powerful cycle. So let's sum it up. Capacitors store and release electrical energy. This makes them essential for things like timing circuits and for filtering out unwanted electrical noise. We measure their capacity in farads, and their symbol on a diagram looks exactly like what they are. Two little parallel lines. And that brings us to our third and final hero, the inductor. Now this one's a little different, because this one plays with the power of magnetism. An inductor is usually just a coil of wire. That's it. But when you run an electrical current through that coil, something amazing happens. It creates a magnetic field. And the inductor stores its energy right in that magnetic field. It's this beautiful, fundamental link between electricity and magnetism, happening inside our devices all the time. And this is the absolute key difference. While a resistor opposes current, period, an inductor opposes any change in that current. Think of a big, heavy water wheel. It takes a lot of effort to get it moving, right? But once it's spinning, it has momentum. It wants to keep spinning at that same speed. It fights you if you try to speed it up or slow it down. That's exactly what an inductor does for electric current. So that's its job, to be a stabilizer. It keeps the current smooth by resisting any sudden changes. We measure this property in a unit called the Henry, and its circuit symbol looks just like what it is, a little coil of wire. Makes sense, right? Okay, this table brings it all together beautifully. Let's just walk through it. First, function. Resistors just dissipate energy as heat. The other two store it, capacitors in an electric field, inductors in a magnetic one. Now, look at what they oppose. This is the big one. Resistors oppose current flow itself, but capacitors oppose a change in voltage, and inductors oppose a change in current. See that? 3 distinct jobs, all crucial for managing energy. So, when you start combining these 3 resistors, capacitors, and inductors, what you get isn't just a collection of parts. You get the very foundation of all modern electronics. And this brings us right back to that question from the beginning. The reason your smartphone and the power grid have so much in common is that they both rely on these 3 little components, all working together in perfect harmony to control, store, and stabilize the flow of electricity that makes them work. You know, this quote here really just nails it, and it's no exaggeration in the slightest. Without these 3 simple, passive building blocks, the entire digital world as we know it would just be impossible. They are truly the unsung heroes of electronics. And that leaves us with one final question to chew on. We've defined what makes these components passive. They can't create or amplify energy. So that kind of begs the question, what makes a component active? Well, that's where things get really interesting. We're talking about components like transistors that can act as tiny switches and amplifiers, the real brains of our devices. But you know what? That's a story for another time. Thanks for joining me on this explainer.